Hi everyone, here we are here to do our chapter 4 lectures. Okay, so in chapter 4 we're going to learn about three major classes of chemical reactions. We're going to learn what is the importance of water as a solvent, and we're also going to learn how to write equations for ionic reactions. Also, we're going to learn about precipitation reactions, acid-base reactions, oxidation reduction reactions, we call it as redox, and what are the elements in redox reactions, and reversibility of reactions and the equilibrium state. Water as a solvent. Most of our reactions we do in water. So water is a very good solvent. A solution consists of a smaller quantity of one substance, the solute, dissolved in a larger quantity of another, the solvent. In an aqueous solution, water serves as the solvent. Some solvents passively disperse the substances into individual molecules, but water is much more active, interacting strongly with the substances and even reacting with them in some cases. If you look at the electron distribution of hydrogen and water, we can see some differences. So this is the electron charge distribution in hydrogen, which is very symmetrical. Hydrogen, both of these are nonmetals formed from a covalent bond. But if you take the water molecule, there is 2 hydrogens and 1 oxygen. And there is a electronegativity difference. Oxygen and hydrogen, they have different electronegativities, which we're going to learn in a next different chapter. So you can see the red side, oxygen is more electron denser, so it is red in color, and we can say it has a partial negative charge. That's why this symbol negative delta. And then these are the hydrogen sides. 2 hydrogens are blue in color. The hydrogens are partially electropositive. So as a result, there is a difference in electron distribution. So the hydrogen and oxygen, so hydrogen and oxygen bond become polar. So this is how we depict a polarity of a bond with this arrowhead pointing the more electronegative atom, and arrow back of the arrow with a plus pointing the more positive atom. So there are 2 polar bonds, and their bond angle is 104.5. So as a result, the bond polarities do not cancel, but they would add it up, so the water molecule become more polar. This polarity help most of the molecules dissolve in water. Okay, so how is water going to do this? How does the ionic compound dissolve in water? So this is our water molecule. You can see the negative end. This is the oxygen and 2 hydrogen positive side. So there is a difference in electron distribution. There is a negative side and also a positive side for the water molecule. So when you put an ionic compound, for example, sodium chloride, sodium could be considered as plus, and chloride could be considered as negative because sodium is the cation, chloride is the anion. Once you put that into water, that is your table salt, the water molecule comes and the chloride ion will be surrounded by the water molecule. When it does so, the hydrogen end would be facing towards the chloride ion because this is negative, so the hydrogen side is more positive. Okay, so water, since it has an electron density difference, it can separate the chloride ion from sodium. And what happened to the sodium? So this is the sodium ion, positive ion. It doesn't have to be sodium, but any positive ion. Now the negative end of the water molecule is going to surround your positive sodium ion. Okay, so that is why when you put a little bit of salt, table salt, into water, they disappear, right? The powdered sodium chloride will become completely soluble in water because the water does that. It takes the negative ion chloride and the positive ion and surrounded by the water molecules, either the positive end of the water molecule or the negative end of the water molecule. Okay, so ionic compound going to be completely soluble in water with this form. And these ionic solutions, since they have ions in the solutions, you can see they conduct electricity. Now this one here is the distilled water, the first one. Distilled water does not conduct a current since no ions present. Water molecule, even though we say it has a partially positive and partially negative sides of the water molecule, there are no fully formed ions in water, distilled water. Since there are no ions, distilled water will not conduct electricity. And this, let's say this is an ionic solid. In order for electricity to conduct, ions need to be in the solution form, or it should be able to move. So in the solid, it cannot move. So then you can again see there is no electrical conductivity. But if you put these two together, sodium chloride or any ionic compound into water, now since the water separates those ions, now you have moving ions that would conduct electricity. In solution, positive and negative ions are free to move and conduct a current. Okay. Using molecular scenes to depict an ionic compound in aqueous solution. The beaker shown below contain aqueous solution of the strong electrolyte potassium sulfate. So we need to know how to draw the molecular formula for potassium sulfate. Which beaker best represents the compound in solution? Water molecules are not shown. Potassium sulfate. So how do you write the formula for the potassium sulfate? Potassium is +1, sulfate SO4 2-. So it's going to be K2SO4. Okay, now this is ionic compound. You can see positive ion and negative ion. When you put potassium sulfate into water, since they are ionic compound, it's going to dissociate into potassium ions and sulfate ions, SO4 2-. But in our formula K2, since there are K2, meaning there are 2 potassium, you have to put that 2 in front of potassium. So 2 potassium ions and sulfate ion would be in the solution. It's asking which beaker represents the compound in solution. Now A, you can see sulfate ion -2 and 2 positives, they are all bound together. So this is not correct because it's not dissociate into ions. So in the water, water molecules come and surround the molecules and separate them. So that's not correct. And what about B? B, you have a +1 and -2, meaning 1 potassium and 1 sulfate are still intact, which is also not true. So that's the wrong one either. And then in the C, there are 1, 2, 3 -2s, and then there are 6 positives. Okay, so the ratio of potassium to sulfate is 2 to 1. So we can see there are 6 potassiums to 3 sulfate. So it's a good ratio. It's a correct ratio. 2 to 1, so 6 to 3. So this is correct. Okay, and what about D? D has more sulfate. 1, 2, 3, 4, 5, 6. It has 6 sulfate and it has 3 potassium. But 3 potassium, 6 sulfate. But that's not correct, right? Because we know the ratio is 1 to 2 to 1, 2 potassium to 1 sulfate, not 3 to 6 or 1 to 2. So this is also wrong. The last one is also wrong because it's not the proper ratio. And then there were one more question that we need to answer. If each particle represents 0.1 moles, what is the total number of particles in solution? Each particle represents 0.1 mole. So each one is 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1. So there are 9 particles, right, altogether. So each one is 0.1. So then if you have 9 particles, what's the amount going to be? 0.9 moles. Easy, right? 0.9 moles. And then we can also consider, once you get the number of moles, what is the number of particles. Okay, if each particle represents 0.1 mole, what is the total number of particles? So since each one is 0.1 mole, so there are 0.9 moles of particles. 0.9 moles. Okay, and then what is the total number of particles? If you take 1 mole, there are Avogadro number of particles. Remember we talked about Avogadro number? So you can do 9 times 0.1 moles, and 1 mole is Avogadro number of particles, and this 23 that you can see, it needs to be 10 to the power 23. Okay, it's not 1023. Okay, so the number of particles would be 5.420 into 10 to the 23. Determining amount or number of moles of ions in solution. What amount or number of moles of each ion is in each solution? 5 moles of ammonium sulfate dissolved in water. Now first we need to know how to draw the molecular formula. Okay, and then 78.5 grams of cesium bromide dissolved in water. And then this main number of formula units of copper 2 nitrate dissolved in water. Let's look at the first one. We want to find out the number of moles of each ion is in each solution. Ammonium sulfate. What is the formula for ammonium sulfate? Ammonium ion is +1 and sulfate is -2. So when you crisscross your charges, it would be like this, ammonium sulfate. Okay, and this is ionic compound and it's going to dissolve into ions. Let's see how they are going to dissolve. So this is how it's going to dissolve. Ammonium sulfate, you put it into water. So this is a solid, you put it into water. The ions are going to dissociate. Since there are 2 ammonium ions, you have to say 2 ammonium ions plus 1 sulfate moles. So from 1 mole of ammonium sulfate, you get 2 moles ammonium ions and 1 mole sulfate. So you start with 5 moles ammonium sulfate. So if you have 5 moles ammonium sulfate, in 1 mole ammonium sulfate, there are 2 moles ammonium ions. So 5 times 2 would be 10 moles ammonium ion. And then if you take 5 moles ammonium sulfate, you use the ratio 1 mole ammonium sulfate, there is 1 mole sulfate. So that's going to be 5 mole sulfate ions. Next one, now you started with 78.5 gram of cesium bromide dissolved in water. Now this is grams. What do you need to do now? You need to convert grams to moles using the molar mass of cesium bromide. So you start with 78.5 grams cesium bromide and use the molar mass of cesium bromide. 1 mole cesium bromide is 212.8 grams cesium bromide. Okay, and when you put cesium bromide solid into water, since it's ionic compound, it's going to dissociate into ions, 1 cesium ion and 1 bromide ion. Once you find the number of moles, 1 mole cesium bromide has 1 mole of cesium, 0.369 when you do this calculation. And it's the same number of moles of bromide, that's also going to be 0.369. Okay. And in the last one, it's asking you have this many number of formula units of copper 2 nitrate. So how do you write the formula for copper 2 nitrate? So it's given to us copper is +2 and nitrate is -1. So the formula is copper 2 nitrate. Okay, when copper 2 nitrate, put it into water, since it's a ionic compound, it's going to dissociate completely into ions. What ions it's going to dissociate? Copper 2 nitrate going to have copper +2 ions and nitrate NO3 minus 1. When you are writing the ions, you always want to make sure that you write the charges. Now in our original compound, it's copper 2 nitrate, so there are 2. So you have to put 2 like that. Okay, that's the formula and what are the kind of ions it forms. Now we are given 3.42 into 10 to the 22 formula units. And we want to find out the number of moles. We know Avogadro number of formula units are in 1 mole. So we use that to convert to moles. So this is the balanced equation, how we dissociate. 7.42 into 10 to the 22, not 10,022, 10 to the 22 formula units of 1 copper mole. Okay, we know 1 mole of copper has this many number of formula units, Avogadro number. This again need to be 10 to the 23. It's a typo right there. Okay, that will give you number of moles of copper nitrate. So this is how you would do it. 7.42 into 10 to the 22 formula units of copper nitrate, and then you use 1 mole copper nitrate has 6.022 into 10 to the 23 formula units. So that will give you the number of moles of copper nitrate in 7.42 into 10 to the 22 formula units, and that is 0.123 moles. And according to the dissociation, if you have 0.123 moles, it should give you 1:1 ratio of copper. So 0.123 moles of copper nitrate. In 1 mole copper nitrate, there is 1 mole copper. So it's about the same amount. But if you want to find out the nitrate, there are 2 nitrate ions for every 1 copper ion. So if you multiply it by 2, that will give us the number of nitrate ions. Okay. Okay, so we'll start the next session fresh, because it's another important concept that we're going to learn.